Okay, so hope my screen is visible. Today we'll start about the CMOS fabrication process. So basically we'll do the CMOS fabrication process by using two methods. One is weld technique, okay? Either it may be N-weld technique or P-weld technique. And next we'll see for tin tube technique, okay? There is one disadvantage in the N-weld technique, that is latch-up problem. So in order to overcome that, we are going for the twin tube process, okay? First, N-weld process. So this is a basic CMOS process, CMOS technique. If you see, one second, yeah, okay, yeah. Mm. Yeah. So this is my NMOS structure, okay, in P-type substrate. So this is P-type substrate. P-type substrate. In the P-type substrate, you will diffuse means you can use NMOS, and this is body. Okay, this is P plus, and source and drain N plus regions, and gate will be there. And next you have N well. Okay, this is N well, and in the N well, so N well is acting as a, let us take N substrate. Okay, N substrate, you will diffuse source and N P plus regions, and gate, and body is N plus region. Substrate is, as I told you, this is lightly doped P-type P-type material. Okay, lightly doped P-type material. P-type material. Okay. Suppose if it is so this is on the P-type substrate. Suppose if it is N-type substrate, here you have N substrate. Okay. Here you have P-well. Like this you have P-well. You have P-well in this. Okay. So basically, we are discussing about the NMOS and PMOS structure on the P-type substrate. Okay, on the P-type substrate. So basically, this is weld technique. So basically, you are fabricating the MOSFET. You are fabricating the MOSFET by using N-weld technique. Okay, weld technique. Okay, this is my PMOS. This is my PMOS, and this body is there. So body and so source and drain will be there. And so here these are the steps. First, you need to create N well or P well region or channel stop region. Okay. So that means well is nothing but we can call a channel stop region. Why channel stop region? So that means this is NMOS. NMOS here channel will be there. Channel is due to electrons. Okay. And here channel is there. Channel is due to holes. Okay. So if well is not there means whatever the electrons present in this channel, they can diffuse from here to here. Okay. Holes that can diffuse from here to here. PMOS to NMOS. So there should be a well that is acting as a channel stop region. Okay. So here that's why we call as a channel stop region. And for NMOS and PMOS, special region must be created. Okay, in which semiconductor type is opposite to the substrate type. These regions are called wells. Okay, opposite to the substrate type means what? So here, if you see, opposite to the substrate type means here you have P substrate. Okay, so here if you have P substrate, what will is there? So here you have P substrate. P substrate means you have N well. Okay. Suppose if you have N substrate, if you have N substrate, okay, what will be should be there. So here you should have the N substrate means P well will be there. Okay. So that means whatever the well is there, that opposite to the substrate. Okay. So opposite to the substrate. These regions are called, we call as wells or tubes. First you need to create the well. Okay. You need to create the well. And next you need to grow the oxide. Okay. You need to grow the oxide. Why? Because above this there is SiO2 layer, silicon dioxide. This is silicon dioxide. Okay. So you need to grow thick oxide for active regions. Thick oxide for active region means for source and drain, you need to grow thick oxide, and you need to grow the thin oxide for gate oxide. Okay. When we are doing that, you can understand. Okay. So so here this is P well is created in the N type substrate, and N well is created in the P type substrate. There are opposite means if it is P well, N type substrate. If it is N well with substrate, P type substrate. Okay. And next NMOS transistor is created in P type substrate, and P well and PMOS transistor are created in the N-type substrate. So if it is NMOS, it is created on the P-type substrate. Okay, and if it is P, if it is or P well. Okay, so NMOS can be created on the P-type substrate or P well. Okay, or PMOS can be transistor can be created on the N-type substrate or N well. Okay, so here P-type transistor is created in the N well. Okay, if it is N substrate, PMOS will be created, and NMOS will be created on the P well. Okay, and next what you need to do, uh, next that we should define the boundaries to fixed channel stop region. Okay, so that is boundaries. And wells are acting as the boundaries, or we can call as a channel stop region. Okay, this is my first method, first step. Okay, this is my first step. Okay, and second step, thick oxide for active regions. So active regions are nothing but what? So those are nothing but source and drain. Thick oxide for source, and we need to grow the thick oxide for active region, that is source and drain, and thin oxide for the gate region. So thin oxide is grown on the surface through the thermal oxidation. Okay, that thermal oxidation we will see, don't worry. So thin oxide has grown on the surface. Thin gate oxide is grown. Thin gate oxide is grown. Okay, so that is you need to grow the thin oxide in the gate and thick oxide on the active region. Those are source and drain. Okay, and as per circuit, makes a pattern of polysilicon layer. Okay, you need to make a pattern of polysilicon. Polysilicon is nothing but it's type of silicon in terms of crystalline in nature. Okay, that we call as polysilicon. For the gate, we are using polysilicon. No? In place of metals, we are using silicon. So that's why we are making this polysilicon. Okay, and so that means the deposit and pattern the polysilicon layer. Okay, next what you need to do, you need to implant the source drain region and substrates and contacts. Okay, so after creating n plus and p plus region for source and drain substrate, so after polysilicon you need to create the n plus and p plus for source and drain and substrate. Source and drain and substrate, you need to create the source and drain and substrate. Okay, after that, uh, create a window and deposit the metal layers. Final step is nothing but metallization. Okay, metallization for metal interconnects. Okay, metallization is for metal interconnects. Okay, so this is a growing of oxide. This is second step. Thin oxide. Okay, this is second step. Thin oxide for gate and thick oxide is for active regions, and growing the polysilicon, and next creating the n plus and p plus for source and drain. Fourth step, and next last step is metallization. Okay, do you understood any doubts or queries? Shall I move forward? These
Yes, sir.
steps. Okay, yeah. So these steps I'm showing in the diagrammatically I'm showing. Okay, what is my first step? First step is you need to create the well. Okay, so that well is for what? If it is a PMOS, you need to create n well. Okay, for the PMOS, you need to create the n well. For NMOS, you need to create the p well. So now our discussion is this one only. Okay, so that means vice versa. You can see this and you can draw for that means on the n-type substrate you need to grow the p well. Okay, vice versa. Okay, you can assume and you can write your steps and try to understand how we are doing. Okay, so here you see first what is this p-type substrate is there. First p-type substrate. Okay, so this is my p-type substrate. First you need to grow the substrate. Okay, p-type substrate. P-type substrate is nothing but lightly doped region, lightly doped p-type material. Okay, that we already seen in the MOSFET. No, p-type substrate is nothing but lightly doped p-type material, p-type semiconductor. And here n plus is there. N plus means what? Plus is there. This is heavily doped. It is acting as the active region. Those are source and drain. Okay. So here if you see, first you need to grow the oxide. Okay. So p-type substrate. On the substrate you need to grow the oxide. Okay. So what oxides you need to grow? So you need to grow the thick oxide for active region and thin oxide is for gate region. First I am growing the thick oxide. What is this? I am growing the thick oxide. Okay, I am growing the thick oxide. Okay, after growing the thick oxide, There is like in the fabrication, there is the etching will be there. Etching is nothing but there is etching is there. Etching is nothing but removing of selected area is nothing but etching. Okay. So here, next step is etching. Etch the oxide for PMOS. So here I need PMOS, no? Here I need PMOS. Okay. So PMOS I need to make in the N well. Okay. So you need to etch this particular area. You need to etch this particular area. Okay, I need to etch this particular etching. Etching is nothing but selecting the particular area is nothing but etching. Okay, and diffuse the envelope. Diffusion is one method in the fab. So diffusion means you can do like with high temperature you are doing. So you are on the semiconductor you are sending these n-type n-type like impurities. Okay, impurities on the semiconductor with the help of gases. Okay, that is diffusing. That we'll discuss. Okay, so you need to diffuse n well. You need to diffuse n well. N well is created here. Okay, n well is created. So that why? Because here you need n well now. Here you need n well. Okay, n well is created, and next after that you need to etch for the oxide. Okay, H for the oxide. Why? Because you need to grow the thin oxide for gate and thick oxide for active regions, no? So here I need to grow the thin oxide. For this growing, I need to you need to etch this layer. You need to etch this layer. Okay, so this is etching the oxide for NMOS. Okay, NMOS. So before this, you need to grow the oxide. Which oxide? Thin oxide. Thin oxide is for what? Gate. Thin oxide is for gate. You need to grow the oxide. Okay. After growing the oxide, okay. So see here, see the steps. First, well creation, N well creation, and growing the thick oxide and thin oxide, and next deposit the polysilicon. So you need to deposit the polysilicon. Okay. I grown the thin oxide. After that, I need to grow the polysilicon for the gate. Okay. For the gate, you need polysilicon. No. So this blue color is nothing but growing the polysilicon above the thin oxide. Okay, you need to grow the polysilicon above the thin oxide. Okay, after that, you need to etch the polysilicon and oxide. Why need to etch? You need to diffuse the source and drain, no? So you need to etch. You need to etch these areas. Okay, these areas you need to etch. Okay, selected areas you need to etch. Okay, there are etching methods are there that we'll discuss in the coming classes. So this is etching. Okay, etching for polysilicon and oxide, and after that you need to implant the source and drain. Okay, there are two methods you can implant the source and drain. One is diffusion, another one is ion implantation. Okay, diffusion is done at the high temperature. Remember, diffusion is done at the high temperature, and ion implantation is done at the low temperature, that to room temperature. But a specific equipment is required. Okay, you are accelerating some ions. Okay, that n plus regions with some voltage, so that it will be diffused. It will be targeted to this p-type substrate. Okay, so you for this means implanting the sources. So n plus regions for NMOS and P plus regions for PMOS. Okay, so this is for implanting the source and drain. You need to implant the source and drain. Okay, and growing the nitrates. Next, you need to grow the nitrates. Why you are growing the nitrates means when you are doing metallization. Okay, normally how you will do the metallization, depositing of metals means normally like let us take suppose let us take the gold metal only. Gold metal. So how to make the ornaments? So first they will like gold will be available in terms of biscuits. Okay, that way they will heat and they will convert the solid to liquid, and after that they will make based on the design they will make the ornaments. Okay, here also during the metallization either you are using copper. That copper they will melt and they will they will convert the solid to liquid. That liquid when they are pouring without these nitrates, whatever the edges of these oxides are there, that may damage. That may damage the edges of this one, that may damage. So in order to overcome this, first you need to grow the nitrates. Nitrates are acting like a nitrates are nothing but it's like a hard substance only. So that will protect the edges of these oxides. Okay, so you need to grow the nitrates to um, prevent the damage during the metallization, and after that you need to etch. Okay, so for metallization you need to etch the selected area, etch the nitrates. Okay, selected area you need to etch. Okay, and after that deposit the metallization. Okay, and metallization means what? When you are pouring these metals into into the substrate, what happens? This all will be shorted only. It will be all will be in shorted position only. So how means you need to etch no. So that means this is nothing but drain. This is gate and this is source. Okay, like this. This is source and drain. Okay, and here also for P well source and drain. So you need to etch different materials. You need to etch for the metal. And this is my PMOS CMOS circuit. This is my CMOS circuit. Last circuit will look like this. See here, last circuit. This one and this one. This one, and this one. You compare. You got the CMOS. Did you understood how I am doing? First, growing the oxide, thick oxide for the active regions, and H for PMOS. Okay. For PMOS, you need N well. Okay. Diffuse N well. H for oxides. Okay, and grow the thin oxide for gate region and deposit the polysilicon, etch the polysilicon and oxide, and implant the source and drain, and grow the nitrates to prevent the damage of oxides, etch for nitrates, and deposit the metals and etch the metals. Is it fine? Do you understood this process? Any doubts or queries? Waiting for your response.
No, sir.
Okay. Yeah. What about remaining?
Yes, sir.
Okay. 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 So this is the annual technique. Okay. Normally well. Okay. So your task is just you show me. You need to you need to do the same process by uh, N-type substrate. N-type substrate. Okay. N-type substrate means same process. Just here you will get what this is N substrate. Okay. Here you will use N substrate, and here you will get P well. Okay, the same process, just to try to understand and continue the steps, write the steps. Okay, write the steps and draw the diagram by NMOS and PMOS in which substrate means N substrate, N type substrate. Okay, N type substrate means P value you get. Okay, so here N type substrate will come, and here you will get P well. In place of N well, you will get P well. Okay, that you try. And next coming to the basic twin tube process. Okay, twin tube process is nothing but we have seen the NMOS and PMOS structure in the P-type substrate. No, there are some issues. Are there issues? What are the issues? There is some mutual coupling between the NMOS and PMOS. There will be a mutual coupling. Okay, the major issue is nothing but latch up in the CMOS fabrication. Latch up, I told you. Latch up is nothing but basically when I'm explaining the latch up, there is some SCR circuit I explained. SCR is not but silicon control rectifier. So inside there will be there is a low impedance path between VDD and supply voltage. Due to that latch up, what happens? The your CMOS may damage. Okay. So in order to overcome this major issue that is latch up, okay, you are going for twin tube process. Okay, twin tube process. Okay, just to go through the concept of latch up and try to understand why you are going for the uh, from the N well to the twin tube process. Then you can understand. Okay, so to avoid these mutual coupling and latch up issues, we are going for the twin tube process. So the name itself it's there. What is the full form means twins. Twins means what? Two wells will be there. Okay. We already seen no well or tube in the in well technique. We already seen that is nothing but we call as wells or tubes. We are growing the wells or tubes. This is nothing but wells or tubes. Okay. So here in the tune tube process, here you have wells are there. Two wells are there. Okay, we are using we are fabricating NMOS and PMOS by twin tube fabrication process. Okay, twin tube fabrication process. Like there will be N type substrate, and above this there is a epitaxial layer. Epitaxial layer is nothing but this is also an N type semiconductor, N type semiconductor, but this is heavily doped. What is this? Heavily doped. You are growing the N-type semiconductor above the you are growing the highly doped N-type semiconductor above the lightly doped semiconductor. Lightly doped semiconductor. Okay, and here N well is nothing but it is acting as N substrate, and P well is also acting as P substrate. You can diffuse the P plus and N plus regions over the this N well and P well. Okay, so that is twin tube process. So these are the steps. First you need to grow the entire substrate, lightly doped entire substrate. Okay, let us use the n-type substrate. N-type substrate, resistivity of substrate should be higher. Resistivity of substrate should be higher means you know the R equal to what? Rho L by E. Okay, and conductance is reciprocal of resistance. Okay, so n-type semiconductor is lightly doped semiconductor. So lightly doped semiconductor means, so as this is lightly doped semiconductor, conductance is less and resistance is more. As resistance is more, conductivity is also, resistivity is also more. No? Resistivity is also more. So that means resistivity of substrate should be higher. Resistivity of the substrate to be higher the resistivity, lesser the current through the substrate. As this is a lightly doped semiconductor, the conductance is less. As conductance is less, there is a small amount of current will be there. Okay. Did you understood this concept? Any doubts or queries? Shall I move forward? Based on these relations and all those things? Fine.
Fine, sir.
I'm explaining the means steps how to grow the I'm talking about this twin tube process. Okay, twin tube process. Okay, yeah. So this is N-type substrate. In the N-type substrate, you need to grow the N plus epitaxial layer. N plus epitaxial layer. This is the epitaxial layer. I told you, no. So this is lightly doped. This is lightly doped semiconductor, entire semiconductor. You are growing heavily doped. This is N plus layer, epitaxial layer. You are growing the heavily doped N plus layer on the lightly doped N-type substrate. That is nothing but we call as epitaxial layer. Okay, that is having the lesser resistance. Why? Because this is highly doped. This is highly doped compared to substrate. As this is highly doped, conductance is more. As conductance is more, resistance is less. As resistance is less, resistivity is also less. Okay. As resistance is directly proportional to resistivity. Okay. R equal to rho L by. E. Okay. So after that, what you need to do? Substrate is subjected to oxidation. Okay. So why it is oxidation? You need to grow the thick oxide for active regions and thin oxide for the gate region. Okay. After that, need to be subjected to the oxidation. You need to grow the thick oxide. Okay. You need to grow SiO2 layer. Okay. SiO2 layer. This is nothing but it's a insulator. SiO2 is nothing but insulator. So if you say take capacitor, we already seen the MOS capacitor. So it is acting as a dielectric between two metals, two like charge carriers. Okay. So here you are applying positive voltage and here channel is due to electrons that is negative. It is acting as a capacitor only. Okay. So here if you see, this is growing the thick oxide for active regions. And next, etching is it. Etching is nothing but you need to etch selected area. Okay. So SiO2 layer is etched using masking. Masking means what? So this layer I want. This layer I want. Okay. I will I will cover with one masking layer and I will etch this area only. I will etch this area only. Okay. So that is etching is done in using masking and two windows are formed. One window is for N well, another window is for P well. Okay, so one window is for what? N well, other window is for P well. Okay, so two windows are formed. Okay, two windows are formed, and next there is a photoresist mask. You need to cover this by using photoresist mask, and here you need to use P plus diffusion for what? P well, for P well. First window is covered, and thus P type impurities are diffused to form P well. Okay, diffused to form P well. Okay, and next, what is the next process? I think next you can guess. So this P well is formed. Again, you need to cover photoresist mask and N plus regions. You need to diffuse and you need to create N well. Okay. Second window is covered by photoresist mask and then N-type impurities are diffused to form N well. Okay, N well. And next you need to grow the thin oxide. You know, I told you, thick oxide is for active regions and thin oxide is for gate terminals. Okay, so you need to grow the thin SiO2 layer. Need to grow the thin SiO2 layer by thermal oxidation for the gate terminal and grow the polysilicon. Here, blue color is there. Above this, you need to grow the polysilicon. Okay, grow the polysilicon for photolithography or pattern making. And after that, you need to do the etching. Okay, so this part I need this for diffusion of this n plus and p plus and n plus regions for diffuse for these active regions. Okay, so you need to make each SiO2 and polysilicon to implant drain and source. Okay, after that, what you need to do? You need to cover this with photoresist mask and you need to do p plus diffusion for source and drain. P plus regions for source and drain. P well is covered and with a photoresist mask and P plus diffusion is done to form a source and drain region. Okay. Next step you can guess. What is the next step? This is over. This is
No,
completed. Next, you need to mask this one and next you need to diffuse this N well. This N well to cover with photoresist mask. Okay. And N plus diffusion is done to form a source and drain. Last method is what? Metallization. Metallization means you need to do the metallization. Metal to diffuse is done, and you need to do etching of metals. Okay, when the metallization is done, so what happens? Metallization is done, so it will be like all will be in short region. Okay, all will be in short region. So you need to etch. That means should be separated. So how to know? That means you need to etch this metallization. Okay, after that contact formation. So you got a twin tube process, CMOS circuit by using twin tube process. Okay. Did you understood the CMOS process by using twin tube process? Any doubts or queries?
no, sir.
Okay. Yeah. And next we'll discuss this one, photolithography. So what is this photolithography? Means what? It is the process to produce circuit patterns on silicon layer. UV layer is exposed to, is used. Two important steps we are using the photolithography. Those are nothing but photographic masking and it contains information we want to project on the silicon wafer. Okay. Photographic etching. It contains the pattern information which we want to remove from the layer. Okay. So here we are using photographic masking and etching. No? This photoresist mask, whatever the information we want, we are covering with photoresist mask. This is nothing but photoresist masking. Okay. And photoresist etching. Where we did photoresist etching? Before this here, see here, whatever the unwanted layer is there, that we did with photoresist etching. This is nothing but photoresist etching. Okay, so that is, so removing the unwanted material or selected material is nothing but photoresist etching. Whatever the material we want, okay, whatever the layer we want, that is nothing but photoresist masking. Okay, both we are doing in this process. Okay, so that is nothing but we call as photolithography. So photoresist masking is nothing but it contains the information which we want to project on the silicon wafer. Photoresist etching is nothing but what? It contains the information we want to remove from the layer. Okay, there are two types of etching are there that we'll discuss. Don't worry. Wet etching and dry etching. Wet etching means by using chemicals. Okay, there are some etchants are there like sulfur fluoride and some agents chemicals are there. With that chemicals, we'll dip your total wafer into that, and whatever the material you want to etch, that will be etched. Okay, that is by using chemical process. And dry etching means by using we need to expose to UV light. So this is dry etching only we are doing. Okay, we are so dry etching means we are exposing this whatever the unwanted means this selected area we are exposing to UV rays, that will be etched. Okay, that is UV etching. Okay, so this is photolithography. Okay, and next ion implantation. This is alternative. I told you, no, like there are in order to diffuse the ions N plus regions, we need to go for two methods. One is diffusion and ion implantation. Diffusion is done in that high temperature and around 2000 degrees Celsius. We need to pass these N plus regions. That those are N plus sources or P plus sources. Okay, the P plus sources during the IC fabrication. Okay, this an implantation is alternative method of diffusion. Okay, alternative method of diffusion. I told you, no, diffusion process is done at a high temperature, but an implantation is done at a low temperature. Okay, so in the an implantation, what you are doing, higher dopant ions are accelerated so that ions can easily penetrate the silicon wafer. Okay, that we'll discuss in detail. Don't worry. And implantation also we'll discuss. Okay, depth of penetration can increase by increasing the acceleration of voltage. So how much of voltage you are increasing, that much of voltage, the depth of penetration will be there. But special equipment is required for the an implantation. Okay, that is the difference between um, diffusion and an implantation. Okay. This is about today's session. Any doubts or queries?